So we talked about cubic model versions of equations of state, and so that's one class of equations of state that are commonly used. Another approach for equations of state is to use what we call the virial model. And so this is something you saw back in your MEB1 courses. And so with the virial model, basically we define the z parameter, right? Where z is going to be equal to the molar volume at whatever temperature and pressure you're at, the actual temperature and pressure, and we're going to divide that by the molar volume for the ideal gas. Okay? And so what that would be equal to would be your molar volume divided by RT over P. That's what the molar volume would be for the ideal gas. Then if you rearrange this, what you end up with is this. Okay? And so that's what Z is, right? It's describing the ratio between your actual molar volume and the molar volume that would be predicted from the ideal gas. Okay? Now the thing, that's what Z would be equal to. But to make this more useful, we could also describe Z in a different way. And what we could do is we could describe Z as a Taylor series expansion. With respect to pressure or volume. Okay? Alright, and so what we would do here is we would say Z, which by definition is equal to this. We would also say that Z is going to be equal to 1 plus the B parameter times pressure plus the C parameter times pressure squared plus a whole bunch of higher order terms. You go to infinity. Okay? Alright, and so these coefficients that we have here, what they would be describing is, we did a Taylor series expansion, so this is just kind of like a math trick. But as far as the physics, what these mean is this B parameter it's describing the interactions between two molecules. Okay? And so that's why those interactions are multiplied by pressure, because as you increase pressure, that increases the likelihood that two molecules will interact. Similarly, the C parameter here describes 3 molecule interactions. And all the higher order terms would just go on to describe, 4 molecule interactions, 5 molecule interactions, so on and so forth. Okay? So that's all really the virial equation is describing. You could write it in terms of pressure, or you could do it in terms of volume as well. So B prime is not the same as V, or is not the same as B prime is not the same as this. But once again, it's just like another kind of coefficient that's being multiplied by the independent variable. So C prime plus ... Okay? Right, and so this is, a virial model which can be used to describe, how non-ideal your gas is. And so if your gas was behaving ideally, your Z factor would then just be 1, right? And then any deviations from 1 would quantify how non-ideal you are. And so to illustrate this, we could go back to that carbon dioxide data. And so here's the same data, but plotted on the y-axis isn't density anymore. Now it's that Z factor, okay? And the x-axis is still temperature. And so what we see here is that for the ideal gas, it would assume that your Z factor would be the same at all temperatures, right? But for all the other equations of state, we see that they capture these sorts of differences or these sort of deviations from that ideal gas law behavior. Okay, so as we go to lower temperature or as you decrease the volume in your system, non-idealities start to matter.